things are, we know that these things are kind of interconnected, you know, trying to send some kind of signals, right, to the robot. If we look at the robot here, we see what it is, right? So just the same way we see robots. If you bring up the human anatomy, you bring up the our brain. I mean, every one of us here has a brain. Of course, our brains are made up of tiny cells. What happens? What do? They talk to each other. If that doesn't happen, trust me, you're as good as dead, right? So your brain, as a human being, it's able to process information, is able to visualize. Just imagine you looking at an empty space, and then what you're looking doesn't make sense to you. It's more like your brain, you're literally brain dead, right? So your brain has tiny cells that actually talk to each other. And then, of course, when you see like something like a dog, what happens? You can see here in this picture, you see here the neurons. So the neurons actually light up. They help you recognize whatever image that you come in contact with. So they send some kind of like electrical signals to say, hey, you're looking at a dog, or you're looking at your girlfriend, or you're looking at something. It helps you, visualize. It gives you that opportunity to visualize and image things. So when we bring it down to technology, when we say neurons in a neural network, what is a neuron in a neural network? So same thing as it applies to humans, it also applies to machines, it also applies to technology. So a neuron is like a tiny calculator, right? It's like a tiny calculator in the computer's brain. Well, the computer's brain, it could be the motherboard or something. So it's like a tiny calculator in the computer's brain. What does it do? It gets some numbers, does some maths, and sends out a new number. So this time around, it's not working in the anatomy of the human brain, right? So it's working like a machine this time, dealing with numbers, input, output, dealing with numbers. So a neural network is sort of like a computer program that learns by example. So, when you start growing up as a child, starting from, as a baby, you begin to learn how to talk. In fact, when you are born, you can't see. That's what I'm made to understand. I don't have a child yet, but that's what I'm made to understand, that as a child, you can't see anything, you can't visualize. That means there's every possibility that you need to your neurons are not maybe mature enough to kind of send signals to you to say for you to be able to understand or visualize images. So that's exactly what happens when you're a baby. But as time begins, you begin to grow up, you begin to see things around you. You're able to recognize your maybe some of us recognize our mommy first, like, because I mean uh, mommy, and then you call mommy, you recognize daddy, and then you call daddy. So that's just the way neural networks are programmed to. They are programmed to learn, they are kind of like computer programs that learn by example. So as children growing up, what do you see? You see yourself you see yourself imitating things like what they say. You look at, they say this is a car, and you're able to figure out like this is a car and all of that stuff, right? So that's just exactly what a neural network does. It learns by example. So it pretends like your brain cell, but this time is actually it deals with numericals, it deals with numbers, inputs and outputs, it deals with ones and zeros, some ones and zeros. What's the main idea? What's the main idea behind convolutional neural network? What's the main idea? So let's think of CNN as a detective, right? They use some kind of convolutional filters to scan an image. I'm sure, of course, we've seen in some of all these scientific movies where you see they use some kind of facial recognition, some kind of biometric to scan your eyes or something before you can gain access into some very protected, highly protected area, right? So they use some kind of convolutional filters to scan an image. So let's try to get the concept here. You know, these filters automatically learn patterns. You know, of course, we'll be looking at all of these things into much details when we are speaking about the architecture. When we are speaking about the architecture, we'll be talking about the different layers of a convolutional neutral network, which is CNN. Please permit me to say CNN. So I'm going to be using the word CNN most of the times, right? It's not necessarily cable news network. So we're looking at convolutional neutral network. So just in case some persons come in and hear me saying CNN, they don't think we're talking about the cable news network. Getting into it, so CNNs actually build understandings layer by layer, from edges to textures to objects. So let's imagine now recognizing a cat, right? We want to try to recognize a cat. Of course, first you don't start looking at the cat as a whole. You want to see some of the features of the cat before you can now, because of course, our brains are very fast to know, because it has learned over time. So when we see cats, we know this is a cat. When we see a dog, we know this is a dog. But of course, you also need machines, that are learning from the scratch. They need to know, they need to understand the different features of a cat. They need to recognize the different features of a cat. For instance, you can have whiskers. You can have whiskers. Of course, whiskers are those things on their nose where they use as sensory. It's part of their sensory organs, right? They also have ears. They have four patterns, right? So CNN does something called an hierarchy of features. So they do learning based on, they start with the less complex features, and then they do a further deep learning into, more of the complex features. So they do a kind of hierarchy of features kind of thing. And that's why in your CNN, you're doing a lot of like batch processing. You don't want to flood your model with some kind of you don't want to flood the model with a lot of data sets, right? So you're going to do a bit of batch learning. So all of these things we'll talk in details. So for real world images, of course, we know when it comes to understanding, for CNNs to understand images, of course, CNNs they need to be very powerful enough to understand some of these images, right? So your CNNs, like we said, they are special kind of neural networks, right? Built specially for image recognition. So what they are built specially for is just, see and understand an image better. That is the essence, that's the value you get from the CNN. So we also think, let us look at them like eyes of AI. Everybody, we've been talking about AI, right? Of course, we know that they help computers look at images and detect patterns. Of course, some of the features they want to look at of course, you can be dealing with some kind of data sets. And of course, we'll be sampling some of those data sets as we go on in the class. And of course, data sets, you could see things in your data sets. Your CNN can learn things like detect patterns like lines, shapes, objects, just like we humans, as we recognize cats, lion, our parents, that is what CNN does. But like we said, CNN does this in a mathematical way. It runs it in computer codes. That's what CNN does. So at the heart of CNN is something called convolution operations. And of course, this would give us a lot of insights into the different layers of, give us insights into the different layers of the CNN, the architecture of the CNN, right? This is how the network looks at small parts of the image and tries to detect patterns, right? So just as we as humans, we also try to detect patterns, your CNN models are also trying to do the same thing, right? They're also trying to detect patterns. Like we said, you don't want to flood them with a lot of data sets. So you try to maybe use some minimal data sets. You don't want to use a lot of data sets to to do that, right? So let's take for instance, let's come back to this robot, right? Imagine you have a robot brain that wants to look at pictures. Of course, we see this robot is trying to visualize, right? Look at pictures and know what's in them. Maybe you bring like a dog, like a cat, or maybe like a car. This brain is called a convolutional neural network, or CNN. So CNNs are very good. CNNs are very good at looking at pictures just like your eyes. So they are called computer visions, right? They are called computer visions. And of course, instead of seeing like you as a human, they use math and patterns to understand what's in the picture. So let's take for example, just like you going into nursery 1 or nursery 2 and they're teaching you how to write numbers. They won't tell you first to write 7. They won't tell you or write 6. They can tell you, okay, a horizontal stroke and then a vertical line, right? So that's the same way a CNN model works. That's how it learns. So it wants to learn patterns. He wants to, like we said, he wants to learn lines. He wants to learn shapes. He wants to learn objects, and then bring these pieces together to form a big picture. So that's what CNN does, right? So CNN, of course, will recognize digits, shapes from pixels. What is a pixel? I don't know if we've learned that in the previous class. What is a pixel? Of course, we know a pixel is like a single tile in a mosaic. So if we're going to do, if we're going to look at what a pixel looks like, let's Google it. Let's Google what a pixel is. Sorry, give me a moment. So let's look at what a pixel is. A pixel is one part of a picture. Like it's like just one tiny part, one tiny section of a picture. You're not seeing the details of the picture. Just imagine you having taking a picture of yourself. If you look if you look at the properties of that picture, it will show you some things in regards to pixels, right? So let's see what a pixel is. Let's see if we can see pictures on that. So a pixel will not necessarily give you so much details on the picture, right? So if we look at this picture here, if we take a look at this picture here, right? Let's look at this. Are we following? Hello, are we following?
Yes,
Yes,
with
we are following, but you're not sharing your screen out, you know.
Oh,
We're only
I thought
we're only seeing the section one convolutional CNN and CNN architecture.
all right, let me share my whole screen. Sorry, give me a moment. Let me reshare again.
Okay.
How about now? Let me just know if you're seeing my whole screen.
we are still seeing your slide. Yeah, but your mouse is moving around.
Okay, that's fine. That's fine. So let me just walk you through this. So of course, we said a pixel. So can you see my browser now? How about now?
Yes,
Can you see my browser?
yes,
Okay,
yes.
brilliant. Okay, brilliant. So here is a pixel. What is a pixel? A pixel is like a single tile in a mosaic. So for instance, our pictures, you want to see a pixel, you see all these boxes here. One box here is a pixel. So addition of all these boxes will give you a picture, right? So on its own, it doesn't mean much, but together it will form a full picture, right? It will form a full picture. So why does CNN matter for vision tasks? Why does CNN matter for vision tasks? Of course, we know that the traditional neural networks are generalists, but CNNs are specialists in the sense that you can you can now define your CNN to be specific in the area you want it to be trained on, right? You want it to be trained on. Let me get off this page and go back to the slides. So CNNs are specialists in images. Like I said, they are not generalists, right? They are not generalists. So think about looking for a cat in a photo, right? Of course, you don't care where in the image it is. You want to look for some kind of familiar patterns. And for CNNs will kind of like mimic this by focusing on the patterns and their relative positions, not exactly the coordinates. So that is what CNN does. CNNs are more like specialists. And of course, we can't talk about uh, convolutional neural networks without speaking about their architectures. So what are CNN architectures? Right? What are CNN architectures? So CNN architectures are some kind of like blueprints or like a building plan for how the machine is made. So for instance, if we look at this robot, I'm going to be using this robot for illustrations a lot of times. So if we look at this robot, of course, we know that this robot has a brain. I mean, a mathematical brain, if that's what we're going to call it, right? It has a brain. And of course, we know that uh, uh, the brain can be tiny, in the sense that it is fast, very fast, but not super smart. It can be very big and strong with capabilities of seeing tiny details, but takes more time to process. Then we also have a situation whereby it can be very smart with memory in the sense that it can remember things from before, right? So these are blueprints of your architecture, of your CNN architecture. This is how they are made sometimes. They are made tiny, they are made big and strong, they are made smart with a lot of memory. And of course, some of the examples we'll also be looking at going on are architectures are ResNet. We have ResNet, we have VGG, which is Visual Geometry Group, right? Visual Geometry Group. We also have residual networks. So residual networks are some kind of like a super smart brain that can look at really tricky pictures and not get confused, right? It will not get confused. So they are very smart. And then we also have the mobile network. These are kind of like lightweight and optimized for mobile phones and embedded devices. Of course, we know some of our phones have capabilities of facial recognition, right? So these are some of the architectures we can leverage on when building our models. Of course, there are sometimes we can use them as pre-trained if we want to come up with our models using pre-trained models, right? We can use that as well. So let's get into the architecture proper. So for a CNN model, which we're speaking to your VGG, your residual networks, and all of these models, let's look at them like layers, right? So they have like 3 or 4, 5 layers. Of course, your layers can also increase. It could be a multi-layer level. They have, but for the three major layers they have the input layer, the hidden layers, and the output layer. So for the input layer, of course, the input layer is where it receives a lot of data. It receives input of data, and then it's now able to find patterns based on those data. Of course, it's going to transmit that data, it's going to transform that data you send to it to some kind of signals, right? And then you have the hidden layer. So let me just bring it down to a layman term. So let's take a sandwich, for instance. You have your sandwich, you have your bread on the top layer. So let's say the bread on the top layer is your input image. Then I think I like peanut butter a lot. Then you have the peanut butter on the second layer, right? You have the peanut on the second layer, which has lines, maybe objects, right? And then you have the jelly on the next layer, which keeps the shapes. So that is how your CNN architecture looks like. It's architected in layers, right? And of course, this is your architecture. This is your CNN architecture, right? It gets numbers as inputs. What happens? It gets numbers by input, multiplies those inputs by weights, then adds some kind of like a bias, right? So these are some of the things it does, your CNN does, right? And after all the computations, there's something called an activation function, right? Where it's Felix, you have your hand raised. Please go up. Go ahead.
All right, Joseph. Sorry, I don't know if you're actually sharing those parts that you're explaining. You are still on, I think, the 5th slide. That's all we can see here.
Okay, so I'm still trying to give like an intro. So that's why I've not
Okay.
left. Yeah, so I'm still trying to give like an intro into the CNN, right?
All
So I'm
right.
just trying to give a overview of what it is. So of course, we know at the input layer is getting some kind of numbers. And when it gets those numbers, it does some kind of transpose, like it transforms those numbers into signals, right? And of course, it multiplies them by weights. So sometimes the weight could be heavy or it could be light. So when we say the weight is heavy, in the sense that it now knows that this is a cat. So it weighs that object, it weighs that it says, oh, this is a heavy weight. But when the weight is low, that means it doesn't really have an idea of that particular signal. So it doesn't know if that signal is useful, if it is noise, or if it is useful, right? So it multiplies the weight, adds a bias, right, and gets its results. So the outcome is, should I send this number out, and in what form? And that's where the activation functions come in. So we have things like RELU, right? We'll be delving into all of those analogies, right? So how does the CNN structure work with MNIST? How does the CNN structure works with MNIST? I think we should be somewhere around here so that you can follow. Yeah, how does the CNN structure work with MNIST? So the MNIST is short for Modified National Institute of Standard and Training and Technology data sets. So you actually use these data sets to train your CNN models, right? It's kind of lightweight, and of course, when you're using it to train your models, you want to use all of these patterns that we've spoken about. You know, input your data, and then you have your convolutional layers. We'll be talking about all of those things in details, right? We'll be talking about all of those things in detail. So your MNIST, which is your Modified National Institute of Standards and Technology data set, is what you actually use to, you know, train your CNN model. Is a collection of simple, like, handwritten numbers used for training. So let me quickly take you guys to this. Give me a moment. So let me give you a small practical lab on this. But before we go into that, I'm made to understand that some of us are actually using Visual Studio Code. Is that correct?
Yes, sir. Yes, sir.
Okay. Okay, that's fine. Okay, that's fine. So let's, before we actually jump into it, let me just give you let's introduce you into um, convolutional filters, right? What is a convolutional filter? What is a convolutional filter? What is a convolutional filter? So convolutional filters, in the sense that it's some kind of like a small matrix that slides over an image and summarizes local areas, right? So your convolutional filter actually focuses on small patch of pixels at a time. Your pictures are made up of little boxes, pixels, right? And this is what your convolutional filter does. It is a small matrix, that kind of slides over an image. Scanning, convolutional scanning, that's just what it means. Scanning and summarizing local areas. What does it do? It focuses on small patch of pixels. If we remember when we were saying, we were speaking to the traditional neural networks, we say they are generalists. But for the CNNs, they are specialists, right? They focus on the small patches of pixels at a time. They have to learn each of the they want to learn the patterns, they want to learn the lines, they want to learn the objects. They learn these things batch by batch, right? That is what they do. They also the filters also help identify patterns. Like I said, they identify patterns like your vertical line, corners, curvatures, objects, and all of those things. The result of actually applying your filter is called a feature map. What is a feature map? A feature map is like what you call a simplified a version of the image that highlights what the filter detected. So as just as your it's applying filters, scanning, and it's identifying patterns, it's identifying lines, curvatures, corners, it brings all these things together, right? Like we said, as a baby, you start, this is my daddy, this is my mommy, this is my brother, this is my sister. So the same way, your CNN also does the same thing. It's trying to, bring all these features together, right? By after scanning, it brings all these features together to form a feature map, right? So a convolutional filter is like, let us think it like a magnifying glass sliding across an image, right? In those, like in the olden days, like they used magnifying glass, to look at, to read, right? It goes object by object, image by image, focusing on tiny regions and detecting patterns. That's what it does. So like I said, each filter has weights that define what it's looking for. So each of the filter has weight. Filters are also known as kernels, right? So they define what they are looking for. So for instance, when inputting your code, it can be that we're looking for sharp edges, curves, textures. If you look at all those x-rays in the airport, you will see some kind of those scanners, they keep scanning your bag to see if there are some kind of like sharp objects, right? So one of those filters in those scanners will be looking for things like sharp edges, curves, textures. So CNNs, they learn which filters are best for recognizing features, like a nose, a wheel, a cat's fur. So that's what convolutional filters, in other words, kernels actually speak to. So looking at this, a vertical edge like this, if we look at this, we see here a vertical edge filter and a horizontal edge filter, right? So filters, a vertical edge filter will actually light up when it sees stripes on zebra or the side of a building. So it will either lighting up or it will either darken, right? So for edge detection filters, the analogy is like using glasses that only show edges. Of course, you want to use them for detecting outlines. In this case, maybe like security systems that spot intruders based on body shape outlines in dark environments. So this is where vertical edge filters can actually apply. So let's also think of a convolutional filter like a cookie cutter, right? You know that cookie cutter for people like, for some of us who are into the baking industry, right? You want to press onto different parts of the image. You want to press onto different parts of the image to extract patterns, right? Like lines, shapes, right? So let's look at a real world example. Like for instance, your Instagram, right? Your Instagram filters. Of course, they change how the image looks by emphasizing certain patterns, right? That's a real world example. So here, what we see here is a 3x3 filter, right? This is a 3x3 matrix, right? It sees just a tiny patch. Like zooming, just imagine zooming in into like 9 pixels out of an entire face. So if we look at this here, we know that these pictures are not really clear, right? So looking at visual examples of filters. So these are visual examples of filters. These images actually show how different filters detect different features. For example, looking at the vertical edge filter, what has it done here? It has highlighted where strong vertical contrast exists, right? So if we look at these ones here, these are very strong, right? We can see the contrast here. The resolution here is different from what we have here, right? So in other words, so filters just translate raw pixels into useful signals. That's what it does. So when you input into your first layer, your input layer, it transforms that pixel into useful signals. Of course, you know that this is the building blocks of recognition. So let's take, for instance, think of it like this. We're looking at pieces of a picture, right? Just like we're looking at this picture here. Where's that picture here? Right? We're looking at this picture, looking at the pieces of pictures, right? What the CNN does is that it looks at small patches of the pictures, which are the pixels, right? Just like, you know, when you put your magnifying glass over one part of this photo, it will bring out this one of these boxes very big, right? That's what it does, right? Then two, it finds patterns. This is the structure of your CNN. It now finds patterns. It looks for shapes like, you know, like edges, corners, circles, lines, and of course, it's learning. And as it's learning, you know, it's, you know, transcribing, says, oh, this looks like This looks like eyes. This looks like a mouth. This might be nose. Of course, there's no nose here, but this might be a nose. It mixes these patterns together, keeps mixing and matching the pieces to see the big picture. It's just like your puzzles, those puzzles we have, trying to put together a puzzle, maybe a puzzle that has Nigeria on it, you're trying to bring all the states together. That's what the CNN model does. It keeps mixing, matching till the right pieces come together to see the big picture, right? So let's take a step back. We've been talking about CNN. Let's take a step back and think about what happens when you're in a crowd, for instance, as a human being, maybe like in a rally or like in a carnival. And of course, your friend has called you and said, hey, Hassana, I need you to, when you come to the carnival ground or the rally ground, whichever is applicable, when you come there, just I'll be wearing a red hat and an orange shirt. Don't mind my combinations, a red hat and an orange shirt. Just watch out for those distinct features and then you see me, right? So of course, when you get to the rally, you first want to take a step back, right? Then you want to try to spot some of those features that Hassana has told you to spot out for so that you can find her, right? Of course, you might notice other details. You might notice some other details, but it might not be distinct to Hassana. It might be for some other persons that is also within those layers, within the architecture of your CNN model, right? Of course, what happens? Your brain then puts together these details. It says Hassana is wearing a red hat and an orange shirt. Maybe if I see her eyes and her ears, maybe Hassana has frog ears or donkey ears. I'll know that's Hassana, right? And eventually you see Hassana and that's it. So that's exactly how the CNN works. It builds up recognition in steps, first small features, then bigger and more meaningful ones. Unlike your traditional neural networks that can recognize simple images like handwritten numbers, but struggle when things get messy or realistic. So just for instance, Hassana has worn some kind of face masks. It's going to be very difficult for me to see Hassana and know that that's Hassana, right? So for the traditional neural network, it will be very, very hard to conceptualize that image. But for the CNN will be able to bring up those image, see those image. It can work with complex images, complex types. And of course, that's why CNNs are used for computer vision tasks. What are computer vision tasks? Computer vision tasks, like your CNN models, is like teaching computers how to see and understand pictures, right? Like facial recognition, object detection, all those motion cameras. Once you pass them, it's able to, detect, right? Those are some of the computer vision tasks. Even to your self-driving cars, those are computer vision tasks. They are able to see signs, traffic that says green lights. If it's green, then you move. If it's not green, then don't move. Right? So CNNs are detectives. They're kind of like detectives. They look for small clues in pictures. Like we said, like lines, corners, to build up that big picture, right? To build up that big picture. So in simple summary, let me go back to the slide. Sorry. In simple summary, your CNN is a robot's brain for pictures. That's all. Your architecture is how that brain is built to learn and think. And of course, we saw some CNN architectures like VGG, ResNet. So that is what CNN is in summary. Your convolutional neural networks. Are we following? Are we following? Can anyone hear me? Are we following? Do we have questions? Do we have questions?
No,
Hello?
sir. You're doing justice to this, sir.
All right, so can we go ahead? Any
Yes, sir. Yes, sir.
questions?
For now, on my own side, no, sir. I'm flowing with you, sir.
All right, sir. So we also look at so let's get into it. How do filters become layers? We said filters are kind of like, they scan your layers, right? They scan your layers. But now, how do these filters become layers, right? Filters, how do they become convolutional layers, right? Filters are grouped into, of course, they are grouped into convolutional layers, right? So we know for each layer, you can have a layer that has just lines that has been stacked, a stack of lines. And then we have another convolutional layer that has a stack of objects. You want your CNN model to actually learn from the scratch. Like, you want it to be learning small. It can't just start learning big objects. You want to do some kind of batch processing so that it's learning at little by little, right? Of course, we said your filters are grouped into convolutional layers. So each layer looks at a different feature, like we said. So you can stack many layers. With deeper understanding. So think of it like I said, your first layers can be edges. Your middle layers can be shapes. Your final layers can be whole objects. So if we come back to this guy, so this is a Python script. This is a Python script on Google Colab. And of course, when we run this code, this is what we saw, right? This is what we came up with. So what was happening here, we're trying to visualize pixels and filters. We're trying to visualize pixels and filters. What was the objective here, right? We wanted to see how convolutional filters highlight edges and patterns in an image. So if we look at this is the original image gotten from MNIST. This is the original image gotten from MNIST. Of course, MNIST is a data set used to train your CNN models, and it comprises of numbers, right? So this was the outcome, right? We were able to get the edge detection, right? So what did we do here? We used a grayscale image. So as the number reduces, the number it's white, but at the black end it is at the dark end the number increases. Remember, for your CNN models, of course, you want to impute numbers before you transmit them into signals, right? So what we did here, we just added some kind of simple filters, simple filters, right, on this original image. And of course, it has come up with some kind of patterns and design, right? So this is what we have. We have the original image and then the filtered image, right? We have the original image and the filtered image. Sorry, give me a moment. So what's the benefit here? I mean, this is all about convolution process. This is the operations of convolutional process. This is the process for convolutional neural networking. So of course, we've imputed some Python code here, and we've been able to do some filters, right? We've been able to do some filters on the original image. And of course, we use the MNIST data set to train our model here. That's what we did here. That is what we did here. So this is just an overview of what we've been speaking about. This is an overview of what we've been speaking about. Do we have any questions? Any questions before we go ahead? So how can we actually relate what we have done here to CNNs, right? How can we relate this to CNNs? So of course, we know your CNNs are your artificial, are some kind of artificial neural network designed to process data that has grid-like structures such as images, right? So from this code, we've used a 3x3 filter subel. Sorry about all the jargons, but that's what we've done, right? So of course, filters actually learn by the network. Filters actually learn by the network, right? They learn by the network. Of course, we said all of these things speaks to your convolution operation. And of course, we see here in our Python code, we've already applied that code here for this model, right? Filtered _img equals nd image dot convolve. Of course, this is a mathematical expression. You know, convolution layer to actually convolute your layers in the network. So the core idea here of what we have done here is that we have applied filters to this image, original image here, to be able to extract patterns. So from the edge detection here, we are able to see some kind of patterns such as edges or shapes, right? We can see edges or shape. So what the convolutional network does is that it learns these filters automatically, right? It learns them automatically. So of course, you're looking at this basic image. This is the original image. And of course, processing has already been done. There's some filtration that has been done you know, for you to see these patterns, to see this, for you to detect these edges on a grayscale image. Right? So this is how convolutional networks, neural networks behave. This is how they operate. So all of this code written here, takes a picture of the handwritten numbers, makes it black and white, and then finds the edges of the numbers. So all of these original numbers, these are the edges, these are the patterns. And we can also see it here as well. Like if we come back to this vertical edge filters, this is the same thing that has been done here using a 3x3 weight scale. This is the same thing that has been done here as well, right? It has transformed these originals to this. So this is the edge image here. Although the pixels are a lot higher here, right? Are we following? Are we following? Are we following?
That's well with you, Mr. Joseph.
All right, great. All right, great. So this is how you understand the convolution operations. So understanding convolution layers, we've said a convolution layer applies many filters in a parallel to the image. So all of this original image here, of course, automatically we see that all of this image, it has applied one filter for each of this image, for all of them. Of course, each layer is going to discover new and deeper features. So if you want to do another filter on this, it's going to also discover new and deeper features. If we are supposed to, if we add more layers to the original image, right? So early layers actually detect edges, like what we've seen here, detect edges. Middle layers actually detect shapes, while the final layers detect objects. So of course, we've said convolutional layers could be of 3 layers. However, they could be multi-layers as well, right? They could be multi-layers as well. Right? So each layer detects something. So one layer is detecting the edges, another layer is detecting the shapes. So if we see all of these things here, what it has produced here, we can see that it has given us every layer. It has given us the edges, it has given us the shapes, and it has given us a lot of patterns, right? So this stacked approach creates your hierarchy of understanding, just like how your brain processes visual data. So this is what it does. It has stacked all of the layers together to give us a more to give us a lot more understanding. And of course, this is done automatically, right? This is done automatically. So let us actually go deeper into the CNN architecture, right? Into the CNN architecture. So for each layer, for each of the new layer, it is a chance to actually extract more advanced features. If you look at this original image, you are only seeing numbers, right? But the magic of CNN is that they learn which patterns matter without you having to code them manually. So they learn patterns matter. They learn which patterns matter, right? And this is what makes deep learning so powerful and widely used in applications like, your medical imaging, self-driving cars, facial recognition and all of those applicables, right? So looking at this, you want to think of each, layer stack, each convolutional layer stack, a stack of, experts, each having their own specialization in the level of detail, right? So for each of the layer, one has given us a shape, right? One has also given us lines. If we look from if we take a look at this first object here, it has given us a line, right? It has given us a line. And then it can also give us object parts as well. So early layers, the first layers normally recognizes edges. The first layers, they normally recognize edges, but for deeper layers, they recognize full faces or cars, or maybe like a cat. So for instance, for a cat now, it's going to recognize the furs, the car's furs, maybe at the first layer. And then maybe at the second layer, it begins to recognize the eyes and all other, objects. So that's the analogy behind the convolution layers, the convolutional layers. So like I said, for the layers, like they're sieves, like sieves stacked on top of each other, each one filtering, more complex information than the last. So we'll also be speaking about this in pre-trained models. For pre-trained models, you might not necessarily need, because your CNN model has is of maturity and does not need maybe like the first layer, which deals with pretty minimal things like lines. So we'll also be speaking to that when we're looking at the pre-trained models, right? So let's actually understand convolutional layers even more. Let's go back to the slide. Understanding convolutional layers. So like I said, you remember that I said a single convolutional layer can actually extract low-level features. So using your pre-trained model, you might want to, your pre-trained model might not necessarily have, you might block that part where it has to, go back to, filter that particular layer to extract low-level features. You might not necessarily need to do that, right? So a single convolutional layer can extract low-level features, but deeper understanding comes from stacking multiple layers, right? So you want to ensure that your convolutional layers have lines, they have objects, they have different parts of the object or the image you're trying to visualize, right? That's the essence. But at the same time, you don't want to overflog them with a lot of data sets, right? You want to do this using batch processing, like I mentioned. So what's the value of this? The value of this, in essence, is that it allows your CNNs to actually recognize more abstract elements, right? Like the eyes of a cat or the wheel of a car, right? So it does not depend, because if you're dependent on just the low level features, it might not give you at the activation function, it might not give you the necessary information you are looking out for, right? So this is why you need to do deep, you need to, your CNN model has to have a deeper understanding that comes from multiple stacking layers, of course, that will look at things like the eyes of the cat or the wheel of a car, right? So as you begin to build more layers, of course, what happens? The network begins to grow, just like your brain. Like Israel mentioned, your brain is an is a connection of neurons, more like cells. And of course, there are a lot of complexities in the brain, right? So as you begin to build more layers within your CNN model, it grows in complexity and learns even more, right? It learns even more. So building from lines to shapes to object parts to the entire object, right? To the entire object. So that's what you can also do. Then we also have the multi-layered CNNs and pooling layers, right? So what does this entail, right? As you begin to add more layers, you want to go from simple to complex patterns. But of course, you also need to reduce the image size using pooling layers, right? What does pooling do? So pooling kind of like, helps you reduce the number of details while keeping the most important features. That's what pooling does. And of course, they are of two types. They are of two types. We have the max pooling. The max pooling keeps the highest value, while the average pooling computes the average. So what pooling does is it makes the model faster, more efficient, and less sensitive to exact position of objects. That's the value you get from pooling in your CNN models. So let's take for instance, you're trying to, let's look at pooling from your X-ray, right? From your X-ray. So if you want to get max pooling keeps, of course, the strongest feature, like a bright spot on your X-ray scan, and that's what it does, right? So in terms of your layers, you want to stack your filters in layers. Each layer finds more detailed features. And of course, then you want to shrink the size of the image while keeping the important parts. That's called pooling. So pooling is some kind of like zooming out or keeping focus on the key details. And of course, we see that on some of your video surveillance cameras, right? We see that on some of your video surveillance cameras. So that's the concept of pooling, right? Any questions? Any questions before we go ahead? Any questions before we go ahead? Hello, any questions before we go ahead? Okay, I'm going to call on someone now and ask someone to tell us what we've been saying all along. Hi, Mary, are you there? Hi, Mary, do you want to tell us what we've been talking about, speaking to? Can you give us a summary of what we've spoken about in terms of convolutional neural networks models? What have we been saying? Hi, Mary. David.
Yes, good morning.
Okay, good morning, Mary.
Yeah, so I'll just I'll just say the little I got from what you said. So you talked about neural networks, and we mentioned that neural network is like a network that sends information to the brain. You talked about the fact that CNN breaks objects into smaller parts and try to detect patterns. You mentioned that CNN as specialist in images.
Okay.
Yeah.
Okay.
And
Thank you. Okay. Anyone? Can someone pick up from where Mary stopped? David? David, do you want to try? David?
Hello, sir.
Okay. Yeah, David, I can hear you. Please. Can you pick up
Okay,
where
sir.
Mary stopped?
All right, sir. You talk about pixels, like the smallest unit of a picture, and CNN, we have to look at every pixel in an image that is going to classify to look at it at the pixel level so that it can be able to get and gather all the necessary information needed, all the features and attributes that are related to that picture, like color, size, and others, for you to be able to classify very well. And you also talk about pulling, which you just left. So how CNN is very good at pulling, and it has to pull many different features that will help you to be able to learn an image very well, for you to be able to classify the image very well. So you
Okay,
talk
brilliant.
about ReLU, which is an activation function that is applied in the hidden layer while carrying out its pulling.
Okay,
You
brilliant.
as
Thank
well
you.
talk about filter,
Okay.
so which is part of the features that it perform. Filter is performed for the algorithm to be able to learn some features about the data for it to be able to perform well. Thank you, sir.
Okay, thank you. Thank you so much, David and Mary. Thank you. Thank you for your response. So just to look at also pulling, right? So pulling is like, let's take for instance, you're looking at your room from a far away distance, or maybe you're in a football pitch. Of course, you can tell that there are players on the field, but you can't tell which player is on the field, especially if you're sitting from a position where you can visualize the images of the players, right? Of course, we might tend to like maybe use our phone or something, for some of us with very powerful phones that have that you can zoom in. So that's what pulling is, right? That's what pulling is, right? Of course, we also have max pooling and average pooling, like we discussed. Then we also spoke about, we also have what we call multi-layered CNNs and pooling layers. We also have multi-layered CNNs. Of course, we know that in real CNNs, you typically see some kind of patterns. You see patterns like convolution, ReLU, pooling, convolution. So, this is like a continuous, process, right? As the image, moves through the network, it shrinks in spatial size, but gains more features. It gains depth. It has more features, right? And what do we call this? This is called like a pyramid architecture, right? It's wide at the base, narrow at the top. So let's look at it like funneling a wide view into a focused decision. High input, you have high input, you have compact output. So an example of something like this is, processing a high resolution image with fewer but more meaningful features. And of course, this is what your CNN, your CNN model does. And after all of these processes have been done, then we have what we call ReLU. Your ReLU is your activation function, right? ReLU in the sense that it's your rectified linear unit. What is your rectified linear unit? Hi, David, please go ahead. David, your hand is raised.
All right, sir. Yes, sir. You talk about pulling as kind of zooming in. So
Yes.
the question I have is there a relationship between pulling and pixel, or are they the same?
Between pulling and the pixel. So the pixels, what the pixels does is immediately your model receives your pixels, it transcribes them into signals, right? Remember, that's what we said. It transcribes it into signals, right? But for pulling is a lot is different from pulling is a lot different from I mean, they have some similitudes, but of course, pulling is different. So what pulling does is pulling kinds of like, takes the strongest feature, like picks the good signals and throws off the bad signals. So for instance, let's take for instance Instagram, your Instagram, what's it called? Your Instagram picture, like or let's take for instance, you take a picture on your phone and you take like a burst of pictures. So that burst of pictures your phone takes, you want to your phone automatically picks the best out of that picture, right? Out of the burst of those pictures and discards the rest. So that's what pulling looks like. So pulling keeps the strongest feature like a bright spot, just like you have on an X-ray. Right? So in terms of your pixels, what the pixel is, of course, when you receive an image, it transcribes it into signals. So that's entirely different from what pulling does. Is that clear, David? Hi, David.
Yes, sir. Yes, sir. Thank you, sir.
All right. Thank you, David. So real world. So we're speaking to multi-layered CNN, right? Like following a wide view into a focused decision, high input and then compact output, right? So we said a CNN processing high resolution image with fewer but more meaningful features near the end. And of course, after your convolution process, we now speak about the activation function, which is an abstraction, like you said, in your hidden within the hidden layers, right? So what ReLU is rectified linear unit. And what is rectified linear unit? It's kind of like an activation function you actually use in your neural networks. That is your CNNs. What does it do? It actually helps your model, decide which information to pass forward and which to ignore. So your ReLU is some kind of like a filter that blocks, let's say, blocks negative vibes, only passes signals that are useful, right? Maybe you want to pass signals, strong signals like, distinct edges, while ignoring noise in a blurry image, right? So that's what it does. So if we want to split the name into two, like linear units, rectified linear units, there are two different things. So for linear units, it's like a straight line. more like a single function, right? So your linear functions don't actually help neural network learn complex things. So they are not useful to your model. They are kind of very simple. But in terms of rectify, of course, we know it means to fix that linear parameter, fix that, adjust something. So you want to fix that line so that all negative values become 0. And we know that it's either you have a scale of 0 to infinity, right? And when we combine the rectified linear units, it's a function that keeps all positive values the same. That is, keeps them linear and turns all negative values into 0, rectified. So you don't have any negative value in ReLU. Unlike some other activation functions like sigmod, right? So for ReLU, you have no negative value. You want to discard all negative value because they are bad signals, they are weak signals, right? Why do you want to, of course, we want to ignore the bad negative signals, like I said, and want to focus on the useful ones. Of course, the positive ones we know are the useful ones for the ReLU, right? And that is what the activation function does in the abstract hidden layer, right, of your model. And of course, we know that for ReLU, it's going to speed up learning because it's going to be discarding a lot of negatives. It will speed up learning. And of course, we know that what happens, the network will definitely stop wasting time on unhelpful patterns that are not needed. Also adds simplicity, keeps numbers from getting too crazy, like multiplying negatives on negatives on negatives, you want to, it does that as well, right? Only keeps only the flats that matters. And these are some of the things that your ReLU does. Of course, your positive signals we know often correspond to your real features, like your edges, your corners, your textures. That's what it speaks to. That's what it speaks to, right? But your negative signals, we know they are noise, errors, or confusing data. We don't want our models wasting time on, right? So that's the concept of ReLU, right? That's the concept of ReLU. Any questions? Are we good? All right. So that's that on rectified linear unit. That's that on rectified linear units. Okay. Someone wants to say something? Okay. So that's that on rectified linear units, ReLU. So we've been speaking about signals. What do you understand by these signals? So let's look at signals in this sense. So think like this. Just imagine you give your CNN an image. What does it do? Of course, we know it turns that image into a number, right? Immediately your CNN receives that image, it turns that image into numbers, right? And of course, what do these numbers now do? They travel through neurons. of course, if we look at this robot here, we see that he's trying to visualize something, right? We see he's trying to visualize an image. And of course, as soon as that image hits his iris, it turns into a number. Of course, we know that these numbers, travel through neurons, all of these things, neurons. And at each neuron, of course, we know what we're doing. We're multiplying weights, we're adding things up to get a result. So like I said, for weights, we know what weights are. We know that when we're speaking to weight, we're speaking to how the CNN model really has been able to, visualize and understand all of these objects, lines, edges. It does some kind of weight, like some kind of weighing to know what it understands. Of course, your signals could be positive or they could be negative, like we mentioned in the case of ReLU, your rectified linear unit, right? So that is what signals are, right? So for instance, let's say your neuron gets a signal of, your CNN model gets a signal of plus 4.5. Of course, we know that's a strong positive signal, right? It's speaking up. Or if it's a minus 2.1, we know that's a negative signal. So we know that the minus 2.2 wouldn't be needed, right? So we've been speaking about pooling layers, right? We've been speaking about pooling layers. And of course, we can also, we've also talked about MNIST, and there's also another data set that you can also use to train your model, which is the CIAR10 data set. And what is the CIAR data set? It's the Canadian Institute for Advanced Research data set. Of course, they have real images in their data set, unlike the MNIST, which has numbers, right? 0 to 9. But for the CIFAR is a standard data set used in training your CNN. And what does it contain? It contains about 60,000 small 32 by 32 pixel color images in 10 categories. So of course, this is a much elaborate data set, right? This is a lot. This is a more elaborate data set, right? So it's kind of like a step up from the MNIST. The MNIST digits, of course, it's a step up from them. For the CIFAR 10 has more color, unlike the MNIST that has a lot more black and gray scale. It has more color, more complexity, and of course, it has like 3 channels, right? Give me a moment, please. Yeah, so of course we've also spoken about we've been talking about CNN, the architecture, right? We've been looking at some of the examples of architecture they have. We've looked at VGG, we looked at ResNet. We also have LeanNet architecture, right? We also have the LeanNet architecture, just like your CNN model. This is also simple, but effective. We also know you can use this as your as pre-trained models while you are trying to come up with your own models that are specific to some of the tasks you want it to do, right? Of course, we know the linear architecture was used in the early days of deep learning for digits and object recognition. And it also follows the same logic, right? The CNN model logic, convolution, what we've been speaking about, filtering, future imaging, ReLU, activation functions, pooling to your dense layer, you know. But one thing we also need to note is that training on CIFAR 10, because they especially deal with some kind of like a lot of like large data sets, you are going to need some kind of very high compute, more like a GPU acceleration when training using those data sets, right? Because if you use your normal CPU, it's going to take a lot of hours and days to process, right? Then we also we're looking at pyramid architecture. Pyramid architecture. What is pyramid architecture? So your CNNs are often designed as pyramid, wide at the input layer and narrow at the output layer. So early layers, you're looking at the entire image in detail at the early layers. But as you begin to move deeper, of course, we know that the image gets compressed with features becoming richer. More filters, are now used as you begin to go deeper to capture complex interactions. So let's look at it. Think of it like this, like summarizing a story. You go from a lot of words to like a single conclusion, but with more meaningful packed in. So at the end of this training, of course, we know we'll have like a summary of everything we've been speaking to. And that's what we call the pyramid architecture. So the pyramid architecture in action looks like, you want to start with a few filters, looking for, lines, strokes. Then as you begin to go deeper, the number of filters then increases and the spatial dimensions, of course, will shrink. And of course, one popular example of this is your VGG architecture, right? Your VGG architecture. And if we want to look at this in a business use case, like I mentioned earlier, your airport security x-rays, what do? Of course, they look for certain things. They are trained to look for certain objects or shapes, like knife. What they do is they then combine this feature to get a feature image, right? More like handle plus the blade plus the knife. Then, of course, they decide an action, right? So that's the whole point of the pyramid architecture. And that's what we see in this business use case, right? So what are some of the best known CNN architectures we have, right? We have the VGG, like we've mentioned, which is the visual geometric group. We have the residual networks, and we also have the mobile networks. Of course, we know that over time, researchers are actually developing various CNN models for different purposes. But for the VGG, it's just a simple and effective deep network. And what is it used for? It's great for understanding how CNN works. But for your residual networks, your residual network adds more, shortcut paths to add shortcut paths so that your model can learn faster and better, right? So sometimes your residual network wants to, skip steps like you already understand. Like maybe at a layer one, you might not necessarily, you might skip a layer one, every object or line in layer one, right? Then you also have your mobile network, which is your mobile net. It's a lightweight and it's lightweight. It's a lightweight CNN model optimized for mobile phones and other embedded devices, other IoTs, right? And of course, we know that for your mobile network, we can see some of these things in facial recognition, right? Facial recognition, we can see that is being harnessed adequately, right? We also have your VGG16 group, right? So these are some of the best known CNN architectures, right? These are some of the best known CNN architectures, right? Your mobile net, your VGG, your REST nest. Right, so let's quickly jump into your pre-trained networks and transfer learning. Pre-trained networks and transfer learning. So let's shift into this. Of course, we know that training your CNN model from scratch, of course, is going to take a lot of time. It's going to take a lot of data. But here's a trick. Like I mentioned, you don't have to start from ground zero. You can actually leverage some of the models that has been trained already on large data sets and reuse what they have learned for your task, right? We can do all of that. We can do all of those things using our pre-trained model. So on the practical side, before we get really deep into pre-trained model, we'll be rounding off on this. For pulling visualizations, let me just make this clear. When you're trying to come up with pooling visualization for your CNN model, you want to understand how your max pooling reduces image size and keeps key features. That is some of the things you want to do. Of course, what's the benefits here? It will help you see why pooling makes sense, right? It will help you see why pooling makes sense. Because of our time, we won't be able to do all of these practical labs in real time, right? But I mean, you can leverage some of these points, and we also have. So why do you use? So going back to pre-trained networks, why do you use your pre-trained models? Why do you use pre-trained models? So, of course, we know that training your CNN from scratch is time consuming. We've already established that fact. And of course, it requires massive data. And you know what that means. You're going to be using a lot of processing power, right? And of course, for pre-trained networks, your pre-trained networks offer the solution that you don't have to build from scratch. I mean, these are models, that are already, trained on huge data sets such as ImageNet. And of course, you can also reuse this learning and slightly tweak it for your own problem, right? And you also have something called transfer learning. Transfer learning means, transferring prior knowledge to a new task, right? Transfer learning means transferring prior knowledge to a new task. So CNNs, for CNNs, you want to start with simple shapes and ending with object parts. Of course, you may not necessarily need to, right? There's every possibility you can, utilize pre-trained models. So if a model, for instance, if VGG has already learned what eyes for, wheels look like from a big data set like ImageNet, of course, once you transfer that knowledge to a new task. So you want to go further, like identifying cats versus dogs, because of course, you already have a future image from your VGG, right? So this makes development actually faster, cheaper, and more accurate. So this is very, very important, right? Very, very important. So how do you use your pre-trained models? How do you use pre-trained models? How do you use your pre-trained models? Like we said earlier, you want to use VGG or ResNet trained on ImageNet and applying them to a classification task, right? Of course, you want to leverage libraries like Keras, PyTorch, that will let you upload pre-trained models in one line of code, right? So all of these models, your VGG 1619, your ResNet, your mobile net, which is a lightweight, like we said, and mobile ready for your apps and phones. You can also leverage these pre-trained models. And of course, you can use them. You can also use them as feature extractors. What are feature extractors? When using a pre-trained model, the early layers, like we mentioned, the early layers act as features extractors. What do? They detect general patterns, edges, curves, shapes, right? So you can use this your models, that's VGG, ResNet, as feature extractors. That is, you can also retain only the last layers to classify based on your new images, right? So that's what it does. That's what it does, right? And then we also have what we call cats versus dogs data sets. Cats versus dogs data sets. Give me a moment. All right, so we also have what they call cats versus dogs data sets, right? This is of course we know what this is. It's a of course this is a well-known real world image classification challenge. This is a problem. This is a challenge we actually have, right? And it's a security concern, right? What does this entail? Like, the goal is to tell whether a photo shows a cat or a dog, right? That is the goal of the cats versus dog data sets. You want to tell whether a photo shows a cat or a dog. Sometimes it's surprisingly tricky. You can share many features of a cat and also of a dog. You also want to your pre-trained networks can, be trained on this data set to perform highly accurate classification. And this is some of the things your pre-trained data sets can be trained on, right? So of course, we can now relate it to future extractors. Like we said, for future extractors, you want to detect general patterns, edge, curves, shapes. You want to retain only the last layers to classify based on your new images, right? So we want to actually use those as input to your new classifier so that it's able to mitigate things like when issues like this spring up. You want to use data sets of cats and dogs to see whether it's able to detect which is which, right? Which is which. Of course, for your activation function there, it's possible you can use the sigmoid activation function for this purpose, for your cats versus dogs data set. We know your sigmoid function is zero, it goes from a value of 0 to 1, right? It's either 0 or it's either 1. So the closer it is to 1, it says, oh, this looks like a cat, right? But the closer it is to 0, it means probably like it's not a cat and definitely like a dog, right? So you can also adopt your sigmoid activation function. However, sometimes it might not be possible with your CNNs because sigmoid deals with a lot of binary attributes, right? So it might not be possible. So that's what the cats versus dog data sets actually. So that's it versus cats versus dogs, right? Then we also have cargo, cats and dogs background. Of course, we know the cargo cats versus dog background. We can see this in captures. We can see this in the Alan Turing capture design. Of course, we know this was actually designed to test whether a user was human by identifying cats or dogs, right? However, this is an older kind of an old model kind of thing. I'm not sure a lot of systems, leverage on this as much, right? Then we also have visualizing adversarial cards, right? Visualizing adversarial cards. What does this imply? So here, it's a fascinating trick. You can actually use gradient descent, to generate an image that a neural network is a perfect cat, right? We can use a gradient descent to generate an image that a neural network thinks is a perfect cat. So that is an example here. We can actually start with a blank image and then use the model's response to sculpt a convincing cat. A real world example here is, making an AI dream up what a perfect cat looks like, based on everything it's seen before. So that's what visualizing adversarial cards actually speaks to, right? You also want to improve your visualization. How can you do this? Of course, you can improve your visualization by adding variation loss, That is, you want to encourage neighboring pixels to be similar, right? Making the image smoother, right? What's the loss function here? What does it speak to? Like the loss function, of course, we know is like a thermometer for your errors. You know, it's going to measure how far off the model's guess is from the truth. So you want to ensure that you use this to improve your visualization, right? If the model says cat but was a dog, of course, we know the loss is high. If it gets rice, the loss is low, right? So that is how you improve your visualization, right? Then we also have what we call adversarial attacks. So you can do things. So the thing is, this can be a security issue within your model, right? So for your CNN can actually, you can actually trick it to, like by slightly, altering images, right? You can trick it by altering images, like a concept called adversarial attacks, right? How do you do this? You want to make tiny changes to your cat photo or your dog photo so that the network will misclassify it as something else. So that's what you want to do, right? You want to train it on that as well. You also want to use these images often. You want to use these images like to look like random noise. You want to fool the network. So you can also train it that way because this will also help you understand and improve model security, right? It will help you understand and improve your model security. So like I said, you want to make tiny changes to an image that will trick your CNN into making wrong prediction. So you can change the pixels of a dog's image, and then make the model think it's a cat. Of course, what does this reveal? It actually reveals a vulnerability in your deep learning models. They can actually be fooled even when the image still looks normal to us, right? So that's what the concept of adversarial attack looks like. That's the concept of adversarial attack looks like. So in conclusion, we have learned today what CNNs are. We know they are actually powerful models for image processing, specific image processing, right? They work, of course, how do they work? They work by learning features layer by layer using filters, right? You can, of course, use pre-trained models to save your time, or you can build from the scratch, depending on the dependencies or resources you have, right? I think we've been hacked. You see someone has taken over. So that's it. Of course, we know what transfer learning is, allows you to apply existing knowledge to your new problems. You also need to know that your models can be tricked so that you can ensure security and robustness of your model's capabilities, right? So we've come to the end of the class. Thank you, everyone. Thank you so much for your time. Questions and answers, if we have any. Thank you. Over to you, Emmanuel.
All right. Thank you so much, Mr. Joseph. All right. So if you have any questions, please you can come up with that as we round up the class. And I hope you all filled out the attendance form on the chat box. Also, Mr. Joseph, please can you stop sharing so I can share my screen?
Yeah, we need to do that.
Okay. Okay, so I hope you can all see my screen. This it's a X space round table that's going to be coming up today by 6 p.m. and would encourage everyone to join us. The General Manager, Transformation College, Madam Edith Gochuku, will also be there. So we are inviting you all to join the call and come and while we talk about how to make a healthy workforce environment. I mean, we all know what we're facing in our current workplace. If you're not there yet, you know what you'd want to, how to prepare for what you would face, and um, just join the conversation. It's going to be a really insightful one. It's going to be a great one. I'll share the link on the chat box right now. I'll share the link right now. So that's the link. Please, let's all endeavor to be on the call by 6 p.m. 6 p.m. 6 p.m. Oh, okay. I'm sharing the attendance link again. So please, let's all save that link, this X link for the X space call by 6 p.m. And the attendance form has been reposted. Thank you so much for joining us in today's class. Okay.